For more than 1 billion years after life began, Earth's atmosphere remained devoid of free oxygen. The oceans were green with dissolved iron and sulfides. The sky likely retained a reddish haze of methane. Then, about 2.4 billion years ago, this equilibrium collapsed. Oxygen released by microbes accumulated faster than geological sinks could absorb it. Within a geological instant, the chemistry of air, water, and rock changed. The planet rusted, the haze cleared, and for the first time Earth possessed an oxidizing atmosphere. This transformation, the Great Oxidation Event, set the stage for all complex life to come. Scientists can trace Earth's changing atmosphere through chemical clues in ancient rocks. 1. Before 2.7 billion years ago, the oceans had almost no oxygen and were rich in dissolved iron. Minerals like pyrite and uraninite could survive in river sediments because the air and water were oxygen-free. 2. Between about 2.5 and 2.3 billion years ago, things began to change. Those oxygen-sensitive minerals disappeared, and rusty red rocks started to form on land, evidence that oxygen was appearing in the environment. Sulfur atoms in rocks also began showing unusual patterns that point to a shifting atmosphere. 3. After 2.3 billion years ago, oxygen became a permanent part of the air, though still only a tiny fraction of today's level. This major shift, called the Great Oxidation Event, happened around 2.32 billion years ago, marking the first time Earth's atmosphere held a lasting supply of oxygen. Long before oxygen filled the air, it was being produced in the sea. Cyanobacteria, microscopic architects of stromatolites, had perfected oxygenic photosynthesis. Using sunlight, water, and carbon dioxide, they generated organic matter and released oxygen as waste. For hundreds of millions of years that oxygen reacted immediately with reduced iron, sulfur, and volcanic gases. Only when these sinks became saturated could molecular oxygen escape into the atmosphere. The photosynthetic reaction. Photosynthesis, the process where sunlight turns carbon dioxide and water into sugar and oxygen, can be summed up by the equation: 6 molecules of carbon dioxide plus 6 molecules of water, in the presence of light, produce 1 molecule of glucose and 6 molecules of oxygen. This means that for every unit of carbon taken in, 6 units of oxygen are released. Today, mats of cyanobacteria, tiny photosynthetic microbes, can produce around 10 grams of oxygen per square meter each day. If similar microbial communities had covered the shallow seas of the early Earth, they could have filled the entire atmosphere with oxygen in just about 10 million years, if none of it had been used up. But oxygen didn't build up that quickly. It actually took more than 300 million years, because vast amounts of it were being consumed by chemical reactions with iron and other elements in the oceans and crust. These acted as oxygen sinks, soaking up the gas long before it could accumulate in the air. Molecular fossils known as 2-methylopanes, preserved in 2.7 billion-year-old shales from the Pilbara Craton, record cyanobacterial lipids predating the GOE. These biomarkers confirm that oxygenic photosynthesis evolved well before atmospheric oxygenation. Isotopic fractionations in sulfur and iron likewise show local molecular oxygen oases in surface waters hundreds of millions of years prior to the global shift. Once these sinks filled, oxygen levels began to rise exponentially. Iron in the oceans precipitated as ferric oxides, turning the seas from green to red. Methane, previously abundant, was oxidized to CO, collapsing the greenhouse and cooling the planet. Ultraviolet light acting on oxygen-produced ozone, forming the first stratospheric shield. The air itself transformed from reducing to oxidizing, changing every mineral at the surface and every metabolic pathway in living things. Rocks from about 2.3 billion years ago show the first appearance of red beds, sandstone stained by the rusty mineral hematite. This tells us that iron was reacting with oxygen on land, forming the red color we still see today. At the same time, strange patterns in sulfur isotopes vanished from the rock record. These patterns only form when there's almost no oxygen in the air, so their disappearance shows that oxygen had begun to spread through the atmosphere, reaching at least 100,000th of today's level. Other chemical clues, such as the ratios of chromium and molybdenum isotopes, reveal that rain and rivers had started to weather continental rocks in the presence of oxygen as early as 2.48 billion years ago. Together, these different lines of evidence mark one of the most important turning points in Earth's history, the rise of atmospheric oxygen. The rise of oxygen completely changed the course of life on Earth. Microbes that couldn't tolerate oxygen, called anaerobes, were forced to survive in oxygen-free environments, while new species evolved that could use oxygen to gain energy. The breakthrough was aerobic respiration, a process where living things use oxygen to break down sugar and release energy. In words, the reaction goes like this. 1 molecule of glucose plus 6 molecules of oxygen produces 6 molecules of carbon dioxide, 6 molecules of water, and a large amount of energy. This new way of releasing energy was incredibly efficient, about 18 times more powerful than the old method of fermentation. It was a biochemical revolution that eventually made complex, multicellular life possible. The most striking evidence of Earth's first oxygen boom is found in banded iron formations, or BIFs, ancient seafloor rocks made of alternating layers of silica, chert, and iron oxide that formed between 2.7 and 2.4 billion years ago. In the early oceans, which had no oxygen, iron existed in a dissolved form that made the water rich and murky. When photosynthetic microbes began releasing oxygen, that oxygen reacted with the iron, turning it into solid rust-like minerals such as hematite and magnetite. These minerals sank to the seafloor, forming thick, layered deposits. Over time, this process removed more than 100 trillion tons of iron from seawater, effectively trapping much of the new oxygen inside rock and giving the ancient crust its deep red hues. The disappearance of BIFs after about 2.4 billion years ago shows that most of the iron in the oceans had finally been oxidized, and the seas were starting to clear. The rise of oxygen, while a triumph for emerging life, unleashed profound climatic consequences. Methane, previously the dominant greenhouse gas, reacted rapidly with oxygen to form carbon dioxide and water. Because carbon dioxide is less efficient per molecule at trapping heat, the planet's surface temperature fell sharply. Within a few million years of the atmospheric transition, glacier advanced toward the equator. Earth entered what may have been its first global ice age, a snowball Earth. In an oxygen-free world, methane could linger in the atmosphere for around 10,000 years, acting as a powerful greenhouse gas that helped keep the planet warm. But once oxygen levels rose to even about 1% of today's amount, methane began to break down much more quickly, surviving less than a decade. As a result, the amount of methane in the air plummeted, and Earth lost a major source of heat. This drop in greenhouse warming likely cooled the planet by more than 20 degrees Celsius, triggering global ice ages that left glacial deposits even in what were once tropical regions. Clues to the great ice ages of the early Earth come from ancient glacial rocks, mixtures of pebbles, mud, and large dropstones left behind by melting ice. These have been found in places like Canada, South Africa, and Finland, dating to around 2.4 to 2.2 billion years ago. Magnetic data show that some of these icy deposits formed within 15 degrees of the equator, suggesting that glacier once reached nearly every part of the planet. At the same time, chemical signals in ancient limestone, unusually high levels of the carbon isotope to the power of 1 cubed C, reveal that huge amounts of organic carbon were buried underground. This process would have released even more oxygen into the atmosphere, reinforcing one of the most dramatic environmental shifts in Earth's history. During this interval, roughly 2.4 to 2.2 billion years ago, Earth may have been locked in ice from pole to equator. Oceans froze over, sea ice kilometers thick smothered the surface, and sunlight reflected back into space. Yet volcanic outgassing continued beneath the ice, releasing CO faster than weathering could remove it. After millions of years, greenhouse gases accumulated, triggering a catastrophic thaw. The ice melted in geologic days, the oceans boiled with super greenhouse temperatures, and chemical weathering of the exposed continents reset the carbon cycle. Computer models of ancient climates suggest that if Earth's surface reflected more than 60% of incoming sunlight, global temperatures could have dropped below -50 degrees Celsius, plunging the planet into a deep freeze. Escaping such a snowball Earth would have required enormous amounts of carbon dioxide, more than 100,000 parts per million, hundreds of times higher than today's levels, to trap enough heat for the ice to melt. When the world finally thawed, this dramatic warming left behind telltale layers of cap carbonates, thick deposits of dolomite and limestone laid down quickly on top of glacial rocks, marking the sudden shift from a frozen planet to a sweltering greenhouse world. Chemical clues within these cap carbonates, particularly high levels of the carbon isotope to the power of 1 cubed C, show that huge amounts of buried organic carbon were rapidly oxidized as the planet warmed after the Great Ice Ages. This process released vast quantities of carbon dioxide back into the atmosphere and oceans, driving a powerful rebound in greenhouse conditions. The event not only transformed Earth's climate but also changed the way the global carbon cycle interacted with life, making the planet's atmosphere and climate far more responsive to biological activity from that point onward. Oxygenation did more than freeze and thaw the planet. It transformed mineralogy, oceans, and evolution itself. Over 2,500 new minerals, oxides, sulfates, and carbonates appeared for the first time, giving Earth its characteristic palette of reds, greens, and blues. The chemistry of the oceans shifted from iron-rich to sulfur-rich, paving the way for new microbial metabolisms. Aerobic respiration evolved, providing an enormous energy advantage and setting the stage for complex cells. Computer models of ancient oceans show that after the Great Oxidation Event, Earth seas developed a layered structure. The surface waters contained oxygen, the middle layers had little oxygen but were rich in sulfur compounds, and the deepest parts remained rich in dissolved iron and completely oxygen-free. This pattern lasted for nearly 1 billion years, a period often called the boring billion, when early complex cells, or eukaryotes, existed but struggled to thrive because the oceans lacked enough nutrients. Over time, as iron was permanently removed from seawater, nutrients like phosphate began to combine with calcium instead. This gradual change enriched the upper ocean with the ingredients needed to support more abundant and complex life. Evidence from ancient minerals confirms this great environmental shift. Before about 2.4 billion years ago, certain minerals like uraninite and pyrite could survive in river sediments because there was no oxygen to destroy them. After oxygen began to accumulate, these minerals disappeared and were replaced by rust-colored iron oxides such as hematite and goethite, along with sulfate-rich salts that formed as shallow seas evaporated. The rise of oxygen also caused sulfur-bearing rocks on land to break down more easily, sending sulfate into the oceans. This new supply of sulfur supported a variety of microbes that used it for energy, marking another key step in Earth's evolving biosphere. The GOE was both a catastrophe and an opportunity. For anaerobes, oxygen was toxic. It attacked cellular machinery and generated reactive radicals. Many lineages retreated underground or to anoxic sediments, giving rise to modern anaerobic clades. But a few adapted. Enzymes such as superoxide dismutase and catalase evolved to neutralize reactive oxygen species, allowing new forms of metabolism to thrive. Some microbes turned the poison into power, developing aerobic respiration, nitrification, and sulfur oxidation. These innovations increased metabolic yield by an order of magnitude and prepared the biochemical toolkit that later supported multicellular life. Comparative genomics shows that the genes encoding these antioxidant enzymes are ancient, with duplication and diversification occurring near the 2.4 billion year horizon. Molecular clocks for cytochrome oxidases, the terminal components of aerobic respiration, also cluster in this window, linking molecular evolution directly to atmospheric transformation. By about 2.0 Ga, oxygen levels stabilized at roughly 1 to 10% of present atmospheric levels. The Earth had entered the Proterozoic eon. The sky turned blue under the newly formed ozone layer. The oceans cleared. Continental weathering accelerated. The climate oscillated between mild warmth and deep freeze, but the biosphere endured. Life had survived its first planetary crisis and emerged stronger, armed with the tools to colonize an oxidizing world. After the Great Oxidation Event, the amount of carbon dioxide in the atmosphere dropped sharply as oxygen-rich weathering of rocks began again. In the oceans, levels of sulfate, a compound formed when sulfur reacts with oxygen, increased, while the deepest waters remained low in oxygen and rich in dissolved iron. This partly oxygenated world persisted for more than 1 billion years, a long era of balance between old and new chemical conditions. Eventually, another major rise in oxygen, known as the Neoproterozoic Oxygenation Event, transformed the planet once again, creating the environmental conditions that allowed animals to evolve. The Great Oxidation Event was Earth's first biological revolution. A gas exhaled by humble microbes remade the planet, froze the seas, and rusted the continents. It marked the end of the Archean world and the beginning of the Proterozoic, a planet breathing for the first time. Oxygen would never again vanish. Its concentration would fluctuate, but its presence would define the character of all later evolution. In the next episode, the focus turns inward to the microscopic frontier, the rise of eukaryotic cells and the dawn of complex life.